In this video, we're going to be looking at acceleration versus time graphs. First of all, what is the slope of an acceleration time graph? If you had, for example, an acceleration time graph with a slanted line going up along here, that means that your acceleration is changing. If you were to pick 2 points on that line, you would be getting a change in acceleration over a change in time. And that is really meaningless as a physical quantity. Your slope will essentially have units of meters per second for every second. It's like meters per second cubed. It's how much the acceleration is changing by. So it's like accelerating acceleration. Just as we had in the earlier graphs, if you extended this line and found out the y-intercept, this would represent the initial acceleration. But rarely do we deal with problems that have changing acceleration. Normally, we will have all situations having the same acceleration, what we call uniform acceleration. You're really only going to see horizontal lines. In this case, this is constant positive acceleration. This would be constant acceleration as well, but it would be zero acceleration. And if we have the horizontal line falling below our horizontal axis, then we have constant negative acceleration. So all of our problems that involve constant uniform acceleration will be horizontal lines. If we're dealing with free fall, then the acceleration here will have a value of negative 9.8 meters per second squared. So these horizontal lines mean that we have a constant acceleration. But why do we plot these if they're just all horizontal lines? Well, there is something important that we could get from the acceleration time graph. If we were to get the area under the acceleration time curve, we would find out that it actually represents something. Let's say, for example, we have an acceleration of, say, 10 meters per second squared over a time period of, say, 5 seconds. What would this area represent? Let's take the height of the box, which will be 10 meters per second squared, and multiply by the width of this box, which is 5 seconds, and this gives us an answer of 50. Again, you can see units canceling out, and we will end up with meters per second. And hopefully you're getting an idea what it represents. The area on a velocity time graph, if we have a velocity time graph, when we had something like this and we calculate the area of that represented displacement. But when we calculate the area under an acceleration time graph, it represents a velocity. Initial velocity? Final velocity? What is it? It's really a change in velocity. All right, that might be a little bit confusing. It doesn't tell you what velocity started with or ended with. It just tells you how much it changed by. Remember that the acceleration definition is the change in velocity over the change in time. So if we were to rewrite that, we would have the change in velocity equals the acceleration times the time. Or should I say the time interval? This represents the acceleration, that represents the time, so therefore the area represents the change in velocity. By the way, when the area is above the horizontal axis, that's positive, and when the area is below the axis here, it's negative. Okay, I think you're ready for the next example.